In this problem, we're given a function and we're asked to find the derivative and to simplify the result. So as I look at this function, what I notice right away is that the variable is up in the exponent. This is an exponential function, therefore, and dealing with exponential functions isn't too bad, but they do have their own sets of rules. The simplest, of course, is the derivative of e to the x is simply e to the x. And the chain rule for that is that the derivative of e to some function is, again, the derivative of the outside evaluated at the inside. So it's just e to the function, and then you need to multiply by the derivative of that function. And these two rules, the second one is the chain rule. These two rules here are what I use for every exponential function. Comparing the two, though, we see that this doesn't exactly fit. So the idea is to perform some algebra first before I get to the calculus step, the derivative. Perform some algebra to make this or force this to look like a base e exponential rather than a base 16 exponential. And the algebra step that we're going to use then is standard step. It's the fact that the base e exponential and the base e natural logarithm are inverse functions of each other. If you have e to the natural log of some function, that's the same as this function. And this works in either direction. So if you have some function sitting there and you want to make it look like a base e exponential, you can simply rewrite it this way. So my function g, I'm going to rewrite as e to the natural log of 16 to the 7x minus 2. And then what I'll do is a little bit of algebra on this to help simplify. The 7x minus 2 exponent on the argument in the log can be brought out in front of the log. So I can rewrite this one more time so that it's e to the 7x minus 2 multiplying the natural log of 16. And while this may look a bit more complicated than the original version, it's actually the more calc-friendly form of this. This fits now the form for the chain that you're trying to differentiate. You can pull the constant out of the way. So I can pull the natural log of 16 out of the way and differentiate the 7x minus 2. So the derivative is simply the derivative of 7x minus 2 and then multiplied by the constant that's sitting next to it, natural log 16. And we're done. We're finished with the first step, finding the derivative. To simplify this, again, this is a fairly complicated looking expression. It's a little simpler, easier on the eyes anyway, to rewrite this in its original form. The e to the 7x minus 2 times natural log 16, if you just back up our algebra steps, is the same as 16 to the 7x minus 2. This other portion then is times 7 natural log 16, which is all just a number. You could ask your calculator if you wanted the decimal form for it, but that's it. That's the entire derivative in its simplified form. One of the uses for derivative is to find horizontal tangent lines, places where the function might be turning. If we were looking for an absolute max or an absolute minimum value, those would occur where the function has either a derivative not existing or a derivative that's equal to 0. This derivative exists everywhere. The domain of the exponential is all real numbers, and it is never equal to 0. And since this constant over here is not the number 0, it's never 0.